So just a quick recap of things we've actually looked at so far. So if we were going to shoot a bullet at somebody, apple on their head, we would actually aim above it. And the reason for that is that as the bullet was traveling through the air, the force of gravity would be acting on it and would change its motion. The further you are away, the higher we would have to actually aim. And the reason for that is that the longer the force acts, the bigger the change in motion. So the longer the bullet is flying through the air, the more falling has happened because of gravity. So we got that principle that forces change the motion of a body, but if we look at this glass here, there's no change in motion. It doesn't mean that there's no forces because there's a weight going downwards, but it's balanced by a force coming upwards, which is exerted by the surface. So there's only a change in motion if we actually have a resultant force. We looked at changing motion, so I can, or the contact force, so I can poke something, and that's a distortion force, a contact force, which will make it move. It stops moving, and the reason it stops moving when I do it is that there's a frictional force which actually stops it. So the friction between the surface of the glass and the surface is what stops it. So as soon as I stop the contact force, the frictional force is what changes its motion. We also looked at that the heavier something was, that the less the change in motion is for the same force. So pushing a very light person is going to have a much bigger effect on that person than pushing a very heavy person, and you can see that in rugby games or American football games. The other thing we looked at was non-contact forces, and so we looked at gravity, which can act without being in contact. We also looked at an electrostatic force. So if we used a charged straw and a table tennis ball, we could pull it along. And we looked at magnetic force, so you use magnets and magnetic materials, also non-contact forces. So if I were to put the ball in the glass and put it down on the table, we can see at the moment there's no change in motion of that ball. Hence, we know there's no resultant force. It doesn't mean there's no force on it, because there's gravity going downwards and there must be an equal and opposite force coming upwards. Otherwise, there would be a change in motion. But what would happen if I put some water in the glass? And how might we explain it? So if I put some water in the glass, what actually happens? So by pouring water in the glass, of course, a change in motion. The ball is actually now rising up. So if I look at that now, it's clearly balanced. The ball is being supported by the surface of the water. It's not directly on the surface, it's actually going slightly under the surface of the water. But we do know that the force going upwards, which is called buoyancy, is the same as the force going downwards, which is the weight. And we know that because they're balanced. It's got equal and opposite forces, which are balanced. So what would happen if I were to put something which was more dense than water in? So if I pick up my magnets, for example, and I drop my magnet in there, we can see that it falls to the bottom of the glass. Why does it fall to the bottom of the glass? Because the force going upwards from the water is not enough to balance the weight going downwards, and hence it will fall to the bottom. And once it's fallen to the bottom, it will actually now be suspended. So the upthrust, or the buoyancy from the water, plus the actual force, resultant force from the surface of the glass, is what's now balancing the weight.